Welcome to Joy of Architecture. Today, we're diving deep into something absolutely critical for modern microservices. How they handle, tons of requests all at once, concurrency.
Exactly. It's like juggling, right?
Yeah.
How do these systems keep all the balls in the air?
We'll be looking at how different technologies manage this concurrency, what happens when things go wrong.
Like drop balls.
Yeah, exactly. And crucially, the patterns we can use to build systems that are more resilient, systems that don't just collapse under pressure.
Right. Think of it as peering into the engine room. We'll check out how Java does it with Threadpools, then contrast that with Node.js's event loop and Go's Go routines.
And we'll definitely explore the dark side, things like Threadpool, exhaustion in Java leading to those dreaded cascading failures.
Which leads us nicely into the solution, or at least a solution, the circuit breaker pattern.
Ah, yes, the circuit breaker. We'll see how that works. Maybe look at a specific library like Resilience4j in Java.
We'll cover Resilience4j configuration, maybe an e-commerce example to make it concrete.
Cool, and maybe touch on Node.js options too, like Opossum.
Briefly, yeah. And other resilience tools in Resilience4j as well.
Okay, sounds like a packed agenda. Let's jump in. Java, Spring Boot, microservices first. You mentioned Threadpools.
Right. So in Java, especially with frameworks like Spring Boot, Threadpools are the standard way to handle multiple requests concurrently. Instead of creating a whole new thread for every single request, which is super inefficient.
Resource heavy, yeah.
Very. You have this pre-made pool of worker threads. A request comes in, grabs a thread, does its work, and returns the thread to the pool. Ready for the next one.
And Spring Boot often bundles the web server, right? Like Tomcat or Jetty.
Exactly. You're not deploying to a separate server anymore. Usually the server's embedded. And your choice matters. Tomcat, Jetty, Undertow. They handle threads differently.
Okay, let's break that down. What about Tomcat? It's probably the most common one people see.
It is. Apache Tomcat typically uses something called a thread pool executor. It's fundamentally a thread per request model.
Meaning one thread handles one request from start to finish.
Pretty much, yeah. If all threads are busy, new requests wait in a queue. Spring Boot usually defaults it to, say, 200 max threads, and maybe 10 minimum kept ready.
Okay. Strengths and weaknesses of that.
Well, it's well understood, relatively simple to reason about. Good for mixed workloads, some I/O, some CPU work. But the potential downside is memory. If you get hammered with concurrent requests, having 200 active threads takes up memory. It can become a bottleneck itself.
Right, like during a big sale event or something.
Precisely. You could exhaust the pool.
Okay, so what about Eclipse Jetty then? How does it differ?
Jetty also uses a thread pool. Often it's queued thread pool. It's known for being quite efficient and configurable, still mostly thread per request, but it's often highlighted for handling lots of concurrent connections well, especially long-lived ones. Think WebSockets.
Ah, okay, so maybe better for real-time stuff?
It can be, yeah. The defaults in Spring Boot are often similar to Tomcat, maybe 200 max, perhaps 8 or 10 minimum. Some benchmarks show it having a slightly lower memory footprint in certain scenarios. It's generally good with async operations too.
Interesting. No, Undertow. I hear that one's quite different. Non-blocking I/O.
Yeah, Undertow takes a different tack, built on XNIO. By default, it uses a non-blocking I/O model. This means a small number of I/O threads, often just one per CPU core, handle the network connections. Super efficient.
Just one per core handling potentially thousands of connections.
Exactly. They manage the initial request and response, but if there's a blocking operation like a database call,
something that makes the thread wait.
right, that gets handed off to a separate pool of worker threads. This worker pool is usually larger, maybe like 8 times the number of CPU cores by default.
So I/O threads are like dispatchers, and worker threads do the heavy lifting or waiting.
That's a great way to put it. This makes Undertow really, really good for I/O-bound applications, things that spend most of their time waiting for networks or disks. It can handle massive concurrency with very low resource use per connection.
High throughput, low latency kind of stuff.
You got it. Think financial data streams, real-time bidding, that sort of thing.
Okay, that's a super helpful comparison. Tomcat, the solid all-rounder, Jetty efficient with connections, Undertow, the high-performance I/O specialist.
That sums it up pretty well. And choosing the right embedded server in Spring Boot can actually make a noticeable difference.
Cool. Now let's switch gears. How do Node.js and Go handle this concurrency challenge? They don't use thread pools in the same way, do they?
Not at all, especially Node.js. It's famous for its single-threaded event loop.
One thread. Seriously, how does that even work with lots of users?
The magic is non-blocking I/O. The main thread runs the event loop. When Node needs to do something slow, like read a file or make a network call.
Which would normally block a thread, right?
Exactly. Instead of blocking, Node starts the operation and tells the underlying system, hey, let me know when this is done. It registers a callback function. Then, the event loop is free to handle other requests. When the slow operation finishes, an event gets put on the loop, and eventually the callback function runs.
So the single thread is constantly busy processing events, not waiting around, like a super efficient plate spinner.
That's a good analogy. It makes Node really good for I/O-bound tasks because the main thread rarely waits.
But is it really just one thread? What if something has to block, like, complex crypto calculations?
Good point. Under the hood, Node uses a C++ library called libouv, and libouv actually manages a small pool of worker threads.
Uh-huh. The hidden helpers.
Kind of, yeah. Things like file system access, DNS lookups, some crypto compression, they get handed off to this libouv thread pool. The default size is usually small, like 4 threads, but you can configure it with an environment variable, UV thread pool size.
Okay, so Node is single-threaded for your JavaScript code, but uses a few background threads for heavy-lifting OS tasks. Primarily great for I/O stuff.
That's the core idea.
Oh.
Now Go is completely different again. It was designed for concurrency from the ground up.
Using coroutines, right.
Yeah.
What are those exactly? Are they just threads?
Not quite. Think of them as incredibly lightweight, cooperatively scheduled functions that can run concurrently. They're much, much cheaper to create and manage than traditional OS threads.
Cheaper how? Less memory. Faster to start.
Both. You can easily have hundreds of thousands, even millions of coroutines running in a single Go program without the heavy overhead you'd get with that many OS threads.
Wow. Okay, so how does Go run potentially millions of coroutines on, say, an 8-core machine?
It uses what's called an MN scheduler. It maps M coroutines onto N operating system threads. The Go runtime manages this scheduling very efficiently. Typically, N is set to the number of CPU cores, so GeoMax ProCS environment variable controls this. The runtime figures out which coroutine runs on which core thread.
So it handles the complexity of thread management for you, letting you focus on the concurrent tasks using coroutines.
Exactly. And Go also promotes a specific way for these coroutines to communicate: channels.
Channels?
Yeah. Instead of sharing memory directly and using locks, which can get complicated, Go encourages you to pass data between coroutines using these typed channels. The philosophy is share memory by communicating.
Interesting. So Go is built for massive concurrency, low overhead, great for network services, distributed systems.
So it's a major reason for its popularity in cloud infrastructure and backend services.
Okay, that's a fascinating contrast. Java's configurable thread pools, Node's non-blocking event loop with helper threads, Go's lightweight coroutines and channels. Very different philosophies.
It definitely shows there's no single right way. Depends on the problem.
Right. Let's circle back to Java then, and that risk you mentioned. Threadpool exhaustion causing cascading failures. Paint that picture for us. It sounds bad.
It is bad. Imagine your order service needs to call a payment service. Now, what if that payment service starts responding really slowly? Maybe its database is overloaded.
Okay, so the call from the order service takes a long time to return.
Exactly. The thread in the order service making that call is now stuck, blocked, just waiting.
Okay.
Now, if lots of orders are coming in, more and more threads in the order services pool make calls to the slow payment service, and they get stuck too.
Oh, I see where this is going.
Yep. If the request rate stays high and the payment service stays slow, eventually all the threads in the order services pool are occupied waiting. The pool is exhausted.
So what happens to the next customer trying to place an order?
Their request hits the order service, but there are no threads left to handle it. The order service itself becomes unresponsive. You can't process any new requests.
So order service fails, but you said cascading.
Right, because what if, say, a shipping service needs to call the order service to confirm an order before shipping? Yeah. The shipping service calls the order service, but the order service is unresponsive because its threads are all tied up waiting for the payment service. So the shipping service's request times out. It might start having problems. Maybe its own threads get blocked.
It spreads like a disease through the system.
Precisely. A failure in one downstream service, payment, causes resource exhaustion and failure in its caller, order, which then causes failures in its caller, shipping, and so on. That's a cascading failure. It can bring down large parts of your application.
Yikes. Okay, we need protection. This is where the circuit breaker comes in, right? How does it stop this domino effect?
Exactly. The circuit breaker pattern acts like an electrical circuit breaker for your service calls. It wraps the potentially failing call, like the call to the payment service, and monitors it.
Okay, so it's watching that connection.
Yep. And it has 3 states. The normal state is closed. Think of it like a closed electrical circuit power flows. Requests go through to the payment service, and the circuit breaker just watches, counting successes and failures.
Okay, business as usual. What if failures start piling up?
If the failure rate crosses a certain threshold, say, more than 50% failures in the last minute, and the circuit breaker trips and moves to the open state.
Like flipping a switch off.
Exactly. Now, when the order service tries to call the payment service, the circuit breaker immediately blocks the call. It doesn't even try to reach the payment service.
Ah, so it fails fast.
Right. It instantly returns an error or maybe a fallback response. This is crucial. It stops the order service from tying up its own threads, waiting for a service that's likely still down.
And it gives the payment service a break, right? Stops hammering it with requests.
Absolutely. It prevents resource exhaustion in the caller and gives the failing service time to recover. Now, it doesn't stay open forever. After a configured timeout, say 30 seconds, it moves to the half-open state.
Half open. Cautiously optimistic.
That's a perfect way to put it. In half-open, it allows just a few, like a small number of trial requests, to go through to the payment service.
Testing the waters.
Exactly. If these trial requests succeed, the circuit breaker assumes the payment service is healthy again and snaps back to the closed state. Normal operation resumes.
And if they fail?
If any of those trial requests fail, nope, it decides the service isn't ready yet, and it immediately snaps back to the open state for another timeout period.
That's really clever. It protects the caller, gives the dependency breathing room, and has a safe way to check for recovery.
It's a fundamental pattern for building resilient distributed systems.
So how do we actually do this in Java? You mentioned Resilience4j.
Yes, Resilience4j is a fantastic, lightweight Java library specifically for these kinds of resilience patterns. It's kind of the modern successor to the older Netflix Hystrix library.
Okay, how easy is it to use?
Pretty straightforward. You first create a circuit breaker instance, maybe using default settings or configuring it. You give it a name, like circuit breaker.defaults, payment service.
Got it. A named circuit breaker object. Then what?
Then you need to decorate the code that makes the call to the external service. Resilience4j provides helper methods like decorate supplier, decorate runnable, decorate callable.
So you wrap your potentially failing call with this decorator.
Exactly. You pass your circuit breaker instance and the function or Lambda expression that actually makes the call to the payment service.
And Resilience4j handles the state logic, checking if it's open, closed, half open.
Precisely. When your decorated code runs, Resilience4j checks the state. If closed, it executes your call, monitors the result, success or failure based on exceptions usually. If open, it doesn't run your code at all. It just throws a specific exception, like call not permitted exception.
Which your code can then catch and handle, maybe return a default message.
Exactly. Or trigger some other fallback logic.
Let's walk through that e-commerce example again, but with Resilience4j, order service calling payment service.
Okay, so you wrap the payment service.chargeGuard. Call inside a Resilience4j decorator using our payment service circuit breaker. Initially, the circuit is closed. Orders come in, payments go through fine. Resilience4j notes the successes.
Happy path.
Then, the payment service starts timing out or throwing errors. Resilience4j starts counting these failures. Let's say we configured it to open if 50% of the last 20 calls fail.
Okay.
Once that threshold is hit, bang, the circuit breaker flips to open.
So the next order comes in.
The order service code tries to execute the decorated payment call. Resilience4j sees the circuit is open, immediately throws call min permitted exception. Your order service catches this exception and maybe returns a message to the user. Payment system unavailable, please try again later. No thread gets blocked waiting for the slow payment service.
Much better user experience and protects the order service. What about half open?
Let's say we configured wait duration in open state to 60 seconds. After a minute, the circuit goes half open. We also configured permitted number of calls in half open state to, say, 5. The next 5 attempts to make a payment call are allowed through by Resilience4j. It watches them very closely.
The probe requests.
Right. If all 5 succeed, great. Payment service seems okay. The circuit flips back to closed. Full steam ahead.
But if even one of those 5 fails?
If even one fails, Resilience4j immediately flips the circuit back to open for another 60 seconds. Retry later.
That really makes it concrete. Seems powerful.
Yeah.
Can you customize how it behaves? Like change that 50% failure rate or the 60-second wait?
Oh, absolutely. Resilience4j is highly configurable. You can tune things like failure rate threshold, the percentage of failures to trip the circuit, wait duration in open state, how long to wait before trying half open, sliding window size. how many recent calls or duration of time to consider for the failure rate, like last 100 calls or calls in the last minute.
So you can make it more or less sensitive depending on the service.
Exactly. You also set permitted number of calls in half open state. You can even define what counts as a failure using record failure predicate. Maybe ignore certain types of exceptions.
How do you set these configurations? In code, properties files.
Both are possible. You can define beans in your Spring Boot configuration, customizer beans, to set defaults or specific configurations per circuit breaker name. Or you can set them in your application.properties or application.aml files, which usually overrides the code configuration.
Very flexible. Okay, that's a great look at Resilience 4J. Now quickly, you mentioned Opossum for Node.js. Is it similar?
Conceptually, yes, very similar. Opossum is a popular circuit breaker library for Node.js. You'd wrap your async function calls that interact with external services. It also uses the closed, open, half-open states. You configure it with things like a timeout for the call, an error threshold percentage, and a reset timeout, like wait duration in open state.
Does it have fallbacks too?
Yes, Opossum explicitly supports defining fallback functions that get executed when the circuit is open, which is a common requirement.
So different language, different library, but the same core pattern addressing the same core problem.
That's the key takeaway. Resilience patterns like the circuit breaker are fundamental concepts in distributed systems.
Makes sense. Now, Resilience 4J isn't just about circuit breakers, is it? You mentioned other patterns.
That's right. It's a suite of tools. Some other key ones are retry. Automatically retries a failed operation. Super useful for transient network glitches or temporary service hiccups. You can configure number of attempts, wait intervals, back-off strategies.
Right, so instead of failing immediately, just try again a couple of times.
Exactly. Then there's rate limiter. Controls how many requests you can send to a service in a given period. Prevents you from overwhelming a downstream service, or maybe protects your own service from too many incoming calls.
Like flow control for service calls.
Yep. And bulkhead. This isolates failures. Imagine you have two separate downstream dependencies. A bulkhead can limit the number of concurrent calls to each one independently. So if one service goes slow and ties up its allocated threads or permits,
it doesn't starve the other service of resources.
Precisely. It contains the damage. Resilience 4J has semaphore-based and threadpool-based bulkheads.
Smart. Resource partitioning. Anything else major?
Time limiter. Puts a hard timeout on an operation. If it takes longer than, say, 1 second, Resilience 4J interrupts it. This prevents threads from being stuck indefinitely waiting for a response that might never come.
Which avoids that threadpool exhaustion we talked about earlier.
Exactly. It complements the circuit breaker.
Wow, okay. So combining these patterns, circuit breaker, retry, rate limiter, bulkhead, time limiter, gives you a really robust toolkit for building resilient Java microservices.
Absolutely. You don't necessarily use all of them everywhere, but knowing they exist and applying them strategically makes a huge difference in system stability.
Well, this has been an incredibly insightful deep dive. We've gone from understanding how Java, Node, and Go handle concurrency
Through the dangers of cascading failures.
to the life-saving circuit breaker pattern and powerful libraries like Resilience 4J and Opossum that implement it, plus other essential resilience tools.
Hopefully you listening have a much clearer picture now of why this stuff matters and how you can start building more robust systems.
Definitely. Remember, thinking proactively about failure is key. How could these patterns apply in your projects? What's the biggest risk you see, and how could something like a circuit breaker help mitigate it? That's maybe the most critical takeaway to consider.
Good question to ponder.
Stay curious, keep learning, and keep exploring the fascinating world of software architecture. And of course, don't forget to subscribe to Joy of Architecture for more deep dives like this one. We really appreciate you tuning in, and we look forward to having you join us next time.